All right, let's dive into the world of hydrocarbons. And I get it, the word chemistry might make you think of boring textbooks, but trust me, this is different. This is the secret story behind the stuff that builds our world, from the fuel in our cars to the very food on our plates.
So let me just ask you this. What could sizzling bacon, a stick of butter, gasoline, and a plastic bottle possibly have in common? I mean, they look, feel, and act completely different, right? Well, the answer is actually pretty simple. They all get their start from hydrocarbons. And what are those? Just molecules made of two things, hydrogen and carbon. That's it, simple as that.
Okay, so there are millions of these different organic compounds out there, and chemists needed a way to sort through the chaos. Think of it like a giant library. You can't just toss all the books in a pile, you've got to sort them by genre, right? Well, chemists do the exact same thing, grouping compounds into families based on what they're made of and how they act.
Now, the official science-y name for these chemical families is a homologous series. Sounds a bit fancy, but the idea is really straightforward. Think about your own family. You probably share a last name, you might have similar looks, maybe even act alike in some ways. A homologous series is just like that for chemicals. All the members have a similar structure, which gives them a similar chemical personality.
Take a look at this table. It shows you exactly how it works. Each family has what's called a functional group. That's the little part of the molecule that gives the whole family its identity. You can see alcohols have an OH group, for example. But for today, we're going to keep it simple. We're zeroing in on the first two families, the pure hydrocarbons, the alkanes and the alkenes.
And here's the best part. Once you know the families, you can basically learn to speak chemistry. Naming a hydrocarbon is just a simple two-step code. First, the beginning of the name, the prefix, tells you how many carbon atoms there are. Meth means 1, eth is 2, prop is 3, and so on. Then, the end of the name, the suffix, tells you the family. If it's an alkane, it ends in ane. If it's an alkene, it ends in ene. So a 2-carbon alkane? Ethane. See? Simple.
All right, let's meet our first family, the alkanes. If hydrocarbons were siblings in a family, the alkanes, well, they'd be the stable, predictable, maybe even slightly boring older sibling. They are the solid foundation, the workhorses of the chemical world.
Now, the key word to understanding an alkane's whole deal is saturated. What does that actually mean? It just means every carbon atom is holding on to the maximum number of other atoms it possibly can. All the bonds between the carbons are single bonds. Think of it like every carbon has all of its hands full. It can't grab onto anything else. These single bonds are super strong and stable, which makes them really hard to break.
So let's meet the first few members. You've got methane up top with just 1 carbon. Then look down. Ethane has 2 carbons. Propane has 3. Butane has 4. You see the pattern, right? Each one is just a simple chain getting 1 carbon longer each time, and it's completely saturated with all those hydrogen atoms.
So what happens as these chains get longer and longer? Check out this graph. As you add more carbon atoms, see how the boiling point just shoots up? Why is that? It's because the longer molecules are just stickier. They have stronger attractions between them. And that's why the really small alkanes are gases. But as the chains get longer, they become liquids like petrol. And eventually, they're waxy solids like you'd find in a candle.
Now, because these alkanes are so stable and kind of unreactive, you might think they're not very useful. But actually, that's their secret weapon. Their stability is exactly what makes them so valuable. They don't do much, except burn. And man, do they burn well. This unreactivity makes them the perfect fuels, releasing tons of energy when we set them on fire in our cars and power plants.
And check out this cool chemistry trick. Look at these two molecules. On the left, you've got butane in a nice straight line. On the right, you've got this branch thing called methylpropane. Now, count the atoms. Go on. They both have 4 carbons and 10 hydrogens. They have the exact same formula, but they're built differently. We call these isomers. It's like having the same box of Legos, but building 2 totally different models. Same parts, different shapes, which gives them different properties.
Okay, so if alkanes are the stable, predictable sibling, it's time to meet the creative, reactive, and way more exciting younger sibling, the alkenes. These guys are the real artists, the building blocks of the chemical industry.
The secret to the alkenes? They are unsaturated. This means they have at least one carbon-carbon double bond. And that double bond, that's their superpower. Unlike a sturdy single bond, a double bond is full of extra energy. It's kind of like a compressed spring, just waiting to pop open and react, letting the alkene form new bonds and build all sorts of new things.
So, this is the main event right here. This comparison tells the whole story. Alkanes, saturated with single bonds, not very reactive. Alkenes, unsaturated with at least one double bond, which makes them super reactive. That one little difference in the bond type, it changes absolutely everything and lets alkenes do this special thing called an addition reaction.
So how can we prove alkenes are more reactive? Well, chemists have this awesome super visual test. It's called the bromine test. See, bromine water has this distinct brown color. If you shake it up with a stable alkane, nothing happens. It just stays brown. Boring. But if you shake it with a reactive alkene, that double bond pops open and adds the bromine atoms right in. The bromine gets all used up and poof, the brown color vanishes. It's instant visual proof of that reactive double bond.
Okay, so we've got our stable alkanes and our reactive alkenes. How do we actually use this stuff in the real world? Well, this is where chemistry gets huge, powering these massive industries that literally shape our lives.
So when we get crude oil out of the ground, we get a ton of these long-chain alkanes, which, honestly, we don't have much use for. But what we really want are shorter alkanes for things like gasoline, and we definitely want those reactive alkenes to make plastics. The solution? We crack them. Cracking is exactly what it sounds like. We use super high heat and a catalyst to literally break the long, useless alkanes into smaller, much more valuable alkanes, and, most importantly, those super useful alkenes.
So now that we've made all these small reactive alkenes, what do we do with them? We can do the exact opposite of cracking. We can build. The process is called polymerization. Just watch how the double bond in each one of these little ethene molecules, we call them monomers, breaks open. This lets thousands of them link up, end to end, forming a massive chain called a polymer. And this is precisely how we make plastics like polyethylene.
And it all comes down to the power of one. Not the number you see on the screen, but the idea of it. Just one reactive double bond in thousands and thousands of tiny little ethene molecules is the single key that unlocks the power to build these huge, strong polymer chains that we use for everything from plastic bags to pipes. The power of that one little feature is just incredible. Okay, let's zoom back out for a second and connect all these big industrial ideas to stuff you actually see and use every single day. Because this chemistry, it's happening all around you all the time.
Remember those addition reactions we talked about? Well, here's one you can probably find in your fridge. Vegetable oils are full of unsaturated alkene-like chains, and that's what makes them liquid. To make solid margarine, food companies use a process called hydrogenation. They literally add hydrogen across those double bonds, turning the unsaturated chains into saturated alkane-like chains. This makes them pack together better, and that's what turns a liquid oil into a solid spread.
This map here just ties it all together beautifully. Start up top with hydrocarbons, and you see the two main paths. On the left, you've got the stable alkanes, great for burning. But follow that arrow from alkanes down to cracking, and you see we can turn them into the family on the right, the reactive alkenes. And from there, just look at all the branches. Addition reactions lead to polymers, ethanol, even the margarine we just talked about. See? It all connects. So look, if you take only one thing away from all this, let it be this. The entire difference between a stable fuel and a reactive building block, between an alkane and an alkene, it all comes down to one tiny thing. The difference between a single carbon-carbon bond and a double carbon-carbon bond. That tiny change in structure creates two families with totally different personalities and completely different jobs in our world.
And that leaves us with one final thought to chew on. We've seen the stability of single bonds and the reactivity of double bonds. But carbon can also form triple bonds in a family called the alkynes. So, based on everything we've just seen, what kind of incredible materials and even more powerful reactions do you think might be possible with a family that's even more unsaturated and even more reactive?
The possibilities are pretty fascinating to think about.